Welcome to real-time waveform streaming using direct to RF arbitrary waveform transceivers. With the evolution of DAC and ADC technology combined with fast instrument computer interconnects such as those employed in PXIe, it's enabled the creation of a new instrument architecture. In this talk, we'll perform a teardown of the Tabor Proteus arbitrary waveform transceiver. We're going to explore some of the concepts such as direct to RF microwave signal generation and analysis, multiple Nyquist zone operation, on-chip IQ modulation, and real-time data streaming. So if you work in radar, especially phased array radars, or are interested in electronic warfare techniques, or you're working on the next generation of wide bandwidth OFDM technology such as Wi-Fi 7, 5G, or 6G, you're going to find this session valuable. The Proteus arbitrary waveform family comes in three different form factors. So we have the PXIe version. This is fast, it's got a high-speed bus. You can have multiple channels. Then we have what we call the friendly user interface one. This is the benchtop. It's got a nice GUI. You can create your own waveforms. It's got a keyboard. You can also use it remotely. And then we have what we call the lower cost one, which is a desktop version. It's the same as the benchtop version, but we take away the screen and the keyboard, so it gives you some cost savings or some price savings. And so this is the lower cost one. Each one is designed, though, with wide bandwidth in mind, and we use direct to RF signal generation and analysis techniques. So that's what we're going to focus on as we go through this presentation. You may have noticed on the last slide that the instrument architecture is modular. We put each module in the different form factors, i.e. the PXI, the desktop, or the benchtop. It allows you to scale your instrument in whichever way you want. If you want many hundreds of channels with high speed, you would use the PXI version. If you want a nice, easy-to-use benchtop, you can configure it from 4 to 8 channels. And the same with the desktop, but just without the screen. Each module has multiple instruments within it. With the latest RF DAC and ADC technology, I can have a digitizer and I can have a waveform generator. I can perform FFTs on those. I could perform the FFTs within the FPGA if I wish to get higher speed data transfer or high-speed data processing. I have very deep memory up to 16 gigasamples, so I can store multiple waveforms inside the instrumentation. And for those of you who are interested in doing real-time closed loop, like characterizing an amplifier or doing some electronic warfare techniques, the programmable FPGA allows you to receive signals and then retransmit signals based on the characteristics of the signal that you received. This is the architecture of each module. So here at the top, you can see that we have 4 digital to analog converters and we have 2 analog to digital converters. We can clock these up to 9 gigasamples per second, and we can clock these two at 2.7 gigasamples each, or just have one running at 5.4 gigasamples. The FPGA is the heart of the system. This is where we do all the management of the waveforms, and this is where you can also program it with using our decision block feature. And then we have the PCIe, or the data transfer mechanism, which is a PCI Express Gen 3. So if we go down to the bottom part of the diagram now and just split it out into the 2 main instruments. One is the arbitrary waveform generator side, so this is what would use the digital to analog converters. And the other is the high-speed digitizer, which would use the analog to digital converters. We can create our waveform in any one of these software packages. We can push it across the fast I/O interface up to 6 gigasamples per second. We can store it in the 16 gigasamples of memory. And then the FPGA here is going to manage how we play it out and when we play it out, or what sequences we play it out. We convert it into the real life signal with our 16-bit DAC, and then we push it out. We have the analog bandwidth here of 9 gigahertz. So we allow you to use this 9 gigasample clock in both the first and second Nyquist zone. I've done experiments and I've used it in the third Nyquist zone. The roll off this filter is very slow, so 9 gigahertz is not a hard stop. Then on this side we have a 12-bit ADC. It goes into the FPGA, you shove it up into memory, and you can push it back out to do analysis or make decisions. Or you can make decisions just internally inside the instrumentation using the FPGA decision blocks, as I just talked about. In this demonstration, I'm going to show you how to do that. The setup is as follows. I have Jupyter Notepad here, and this is where I'm going to develop the various scenarios. I have a Proteus arbitrary waveform transceiver here, and then I have a spectrum analyzer over here, and this is where we're going to look at most of the measurement results. I'm generating a 75 megahertz Gaussian pulse using the arbitrary waveform generator. I'm also using our A10120 amplifier here, which is a 30 dBm maximum output amplifier and goes all the way up to 20 gigahertz, so very useful for these type of microwave measurements that we're doing with an arbitrary waveform generator. The first thing I want to do is change the span of the spectrum analyzer to full span. So this is a 13 gigahertz spectrum analyzer, so the sweep we see going across there is all the way up to 13.5 gigahertz, I believe. Right at this side we can see the 75 megahertz fundamental frequency that I created, but also because our clock frequency is set to 1 gigasample per second, I get plus or minus 75 megahertz at 1 gigahertz, 2 gigahertz, 3 gigahertz, 4 gigahertz, 5 gigahertz, 6 gigahertz, and so on. And these are our Nyquist bands. One thing I can do is say, well, why don't we use it in the fourth Nyquist zone? So let me just tune it to 4 gigahertz, and you can see we have a faithful reproduction of the pulse. Now, what the Nyquist theory tells us, and how these things perform, is that the amplitude rolls off. The higher the Nyquist zone you get, the more amplitude roll off, and it usually follows a sin x over x function, as I've explained in different videos. So you can see the amplitude is quite low. Let's put the spectrum analyzer back in full span. One of the things that the Proteus arbitrary waveform generator family have is a very wide output filter, 9 gigahertz. So this is one of the reasons why we see all these different spectral components going all the way up to 9, 10, 11 gigahertz. So the roll off is not just sin x over x, it's actually the roll off of filter that we are observing as well. Now, if we just want to generate a really pure 75 megahertz signal, or maybe 100 megahertz, 200 megahertz, depending on the quantum system that we're trying to generate signals for, the bandwidth of that system may be wide enough to allow some of these components to creep in, thus creating some distortion. So one way to do that is to decrease the filter size, but then we would lose all our opportunity to create signals in the higher Nyquist zones. But if I use the interpolator, switch that on, now you can see I've used a 4x4 interpolator, so our clock is now at 4 gigasamples per second effectively. I still have the signal down here at 75 megahertz. I have a very clean 3.5 gigahertz before we hit this guy here, which is 4 gigasamples. And then finally up here at 8 gigasamples, I can see a clock frequency down there in the center. I have the plus and minus 75 megahertz. This of course is a useful way of improving the fidelity of a baseband signal, but what I really want to do is generate signals directly to RF with my arbitrary waveform generator, so I don't have to bother with IQ modulators or IF mixers and local oscillators. So I'm going to build a new waveform now, which is an IQ waveform, so it doesn't contain just magnitude points like my previous waveform. I'm going to download that to the instrument. Looks distorted now because the instrument is still expecting magnitude only. I'm going to put by 8 interpolation on, still looks distorted. And now finally I'm going to turn on the digital up converter of the Proteus arbitrary waveform generator. I've tuned the center frequency of the arbitrary waveform generator to 3.6 gigahertz. And so what we see here is our 75 megahertz original Gaussian pulse, now modulated on a 3.6 gigahertz carrier. Here is clock minus the 3.6. Here is clock plus 3.6, and here is 2 times clock minus the 3.6. So if I just wheel the marker around here, you can see we've got a pretty nice signal here at around 12 gigs, 12.8 gigs, 12.9 gigs, 13 gigs. And then we have a signal here at 11, and then scrolling all the way down, this is the signal that we're interested in. And don't forget, we've got the bandwidth or the span set of this spectrum analyzer to 13 gigahertz, so that's the signal that we're interested in at around 3.6 gigahertz minus of course the 75 megahertz that we're modulating it with. Let's zoom in on some of those. So let's change our center frequency to 3.12, and you can see the modulated pulse there looks good. Amplitude is excellent. We haven't seen much of an amplitude degradation by using the digital up converter. So this is in essence in the first Nyquist zone of the instrument. We can go higher to the next Nyquist zone, 4.875 gigahertz. And finally, just for kicks, let's take it all the way up to 11.25 gigahertz and see what kind of pulse we get. Again, the amplitude is pretty good. Of course, the fidelity is fantastic because this pulse is made out of thousands and thousands of points. So it's a very good way to create signals at different frequencies, all the way up into the X-band if you want. So with respect to the IQ modulator, here's a block diagram of the system blown up. So you can see that we have two DAC outputs per digital to analog converter, and each one has an IQ modulator and each one has a numerically controlled oscillator. The numerically controlled oscillator, or NCO, is the equivalent of an analog local oscillator, so that's what we use to tune it to the specific RF frequency. And then we put I and Q in, we have some filtering, we have the mixers for the I and Q system here, and then we sum the outputs and we repeat it twice. What this architecture allows us is it gives us three different modes of operation of the modulator scheme on chip. So one mode is the most easiest mode to use because instead of putting magnitude only data in, we put in an interleaved IQ file. So you put in IQ, and it gets modulated. And say we tune our NCO to 3 gigahertz, we get a modulated carrier at 3 gigahertz. But also, we're also interested in multiple Nyquist zone operations. So we'll get a signal at 5 gigahertz. And if our clock is set to 8 gigasamples per second, as in this example, 5 gigahertz is essentially 8 gigahertz minus 3. And then we'll also get one at 11 gigahertz, and that is 8 gigahertz plus 3. And then 16 gigahertz minus 3 is 13 gigahertz. And this is how we get all these different Nyquist frequencies and how we can use a digitizer, which it only goes up to 9 gigasamples per second, create all these different types of higher frequencies. But you can see there's the trade-off, of course, is amplitude. And here is our peak amplitude at 3 gigahertz. And you kind of get a sine x over x. Well, it's not kind of. You get a sine x over x roll-off. So then there's the half mode. You know, when we use it in this mode, the maximum bandwidth we can create with the signal is a gigahertz, which is good for 5G. But we can go up to 2.5 gigahertz of bandwidth if we use half mode. But we have to give up one of these channels. So all the processing is dedicated on one channel now, and you can get 2.5 gigahertz of bandwidth. You can modulate it up to 3 gigs. You can use these higher Nyquist zones, etc. You could feed a mixer system and some filters and put it up to the millimeter wave as well, and get very wide bandwidth signals for a fraction of the cost of a high performance signal generator. 2 mode is another interesting one because it decouples the operation of a lot of these NCO of the NCOs within the system, and so you can, out of one DAC, you can get 2 independent CW frequencies. So you could have 2 independently modulated signals coming from one DAC. So with 1 mode, half mode, and 2 mode, you get a lot of different capability from the arbitrary waveform generator output, which is built into the DAC functionality, built into our DAC implicitly. So we've looked at this side of the block diagram, and we've especially focused on the DAC in the previous demonstration. We've shown how you can use multiple Nyquist zones to get to higher frequencies. We've also shown how you can use interpolation to move your Nyquist zones around if you wish. And then we also demonstrated the IQ modulator and how that can be used to create a fully modulated signal. Next, let's take a look at the digitizer side. And again, we're going to focus on the ADC and how to use the instrument in the multiple Nyquist zones of the analog to digital converter. I'm going to use the Proteus Arbitrary Waveform Transceiver, which we can see here, as an example. It has a 5.4 gigasample digitizer, which gives us an effective digitizing bandwidth of 2.7 gigahertz, which you can see here. And on a lucid signal generator that I've got connected to it, I've got an RF frequency of 1.125 gigahertz at about 0 dBm feeding the digitizer. On the display here, you can see we have the time domain waveform, and you can also see that we have the frequency domain waveform down here. So let's go ahead now and change the frequency on the analog signal generator. And we could choose something higher than the first Nyquist zone of 2.7 gigahertz. So I'm going to enter in 4950 megahertz, about 5 gigahertz. And you can see our carrier now has shifted from here down to here. If you think about it, it follows the rules of Nyquist. So our sample rate is set to 5.4 gigasamples per second. We change the center frequencies to 5 gigahertz, and what we end up with is a signal here at 400 megahertz. If I just invert the display and change the axis, you can see now that it lines up pretty well in the second Nyquist zone with exactly the frequency that I typed in on this line here. And then we can do the same again going up another Nyquist zone, 6525 megahertz. Okay, now you can see the signal shifted again down, and what we need to do now is uninvert the spectrum and just adjust the markings along the bottom, and you can see now 6525 megahertz is just there. And now you see in this third Nyquist zone that the amplitude of the signal has slightly gone down. Frequency roll-off in each Nyquist zone is related to a sine x over x function. So let's take it higher to 99225 megahertz. And now you can see that our amplitude has gone down a little more. But, you know, we can compensate for this. So I've changed the axes and inverted the spectrum again. You can see the DC levels at the top now and not at the bottom. So I originally had the range set to max on our analog to digital converters. I'll set it to minimum. You can see that's given us an improvement of the gain here. So we're at about minus 18 dBm down from the 0 dBm that we had originally, but we're up at 9.225 gigahertz. And finally, let me take it all the way up to 10.350 megahertz. So that's 10 gigahertz. So you've got a signal here, and you can see the roll-off is a lot more prominent, but we are digitizing a signal at greater than 10 gigahertz with a sample rate of 5.4 gigasamples per second. So this is one of the many ways that you can use multiple Nyquist zones to digitize signals higher than the first Nyquist zone, which would be 2.7 gigasamples per second, because our clock is 5.4 gigasamples per second. So far we've looked at the arbitrary waveform generation section. We focused on the DAC. We learned about interpolation, we learned about multiple Nyquist zone operations, and we learned about the IQ modulator. Then we went over to the high-speed digitizer section. We focused on the ADC. We used the ADC in multiple Nyquist zones all the way up to X-band. And what we're going to do now is look at the real-time waveform streaming. So when we stream waveforms into the instrument, they're going to go straight through the interface. They're going to go into a FIFO scheme here. They do not go up to memory, and they go straight out. And this is truly a software-defined radio at this point. You could put, for example, analog audio in here, or digitized analog audio, and we could play it out. We could modulate it up to an AM or an FF band, and it could effectively be a radio station. That's easy. But for the more advanced users, we could have an LTE data stream. We could have a Wi-Fi data stream coming out, so we can be changing bits on the fly. You could change the characteristics of the waveform on the fly as well for different types of peak to average power ratio or adjacent channel power interference. Or if you're working in electronic warfare or radar, you could be putting different techniques in here to fully test out your receiver, because don't forget we've got 4 channels here, so you can adjust the phase and amplitude and time difference on each one of these channels and create some angle of arrival scenarios. To do fast streaming, you need to get data from your computer or your computer's hard drive to the instrument as fast as possible. And the best way to do that is to use the PCI Express format that is within PXIe chassis. So let's look at PCIe. So if we look at this top left-hand corner diagram here, we can see we have a CPU, we have a video card, we have a GPU, we have an Ethernet card, and these are all connected on the PCIe Express bus. And then here in this corner, we have a PCIe extender bridge, which extends this bus out to the instrument chassis. So we're essentially using the same bus that's within the computer. Like if you use LAN or Bluetooth, you know, the times are a lot slower because there's a protocol translation that goes on. You take some electrical signal and some handshaking mechanism and some data transfer mechanism, convert it to another protocol, and then you have to convert it back at the other side. So with PCIe Express, you get much faster speeds. And if we look at the history of PCIe Express, it goes from Gen 1, Gen 2 to Gen 3. And in Gen 1, if you just had one lane, i.e., a single twisted pair on the backplane here, you would get 250 megabits per second. Gen 1 by 8, you're using 8 twisted pairs or 8 differential connectors on the backplane here. And then by the time you get to Gen 3, you're using these smaller connectors up the top here. And Gen 3 by 8 is 7.8 gigabytes per second. So that's quite a significant speed up. If you compare that to USB 3, which is 600 megabytes per second, you can see that using the PCIe Express connecting directly to your computer is the obvious choice if you want to get information to your instrument very quickly without interrupts. In this demonstration, I'm going to show how to use Proteus in the X-band, and for the purposes of the demonstration, I've created a C library that generates various types of CW signal. In terms of frequency, I could adjust the amplitude on the fly, I could adjust the pulse shape, but for the purposes of demonstration and simplicity, I'm just increasing the frequency. So if I run the code now, and you have to wait a second while Python builds all its threads up, and then it starts to generate the sine waves. And there you can see I'm streaming and I'm increasing the frequency as we go along. And then if you have a look at the spectrum analyzer, which is tuned to 10 gigahertz, you can see there's a CW signal there. Now the next thing that I can do is adjust my code slightly, so I generate random frequencies. And then I run it again. And on the spectrum analyzer, the frequencies are jumping pretty fast, so it's hard for a sweeping spectrum analyzer to pick them up. It needs to be more a real-time spectrum analyzer. But if I go over to the scope, you can see the different sine waves jumping to life there. So fast frequency signal switching, X-band transmissions, the ability to change frequency, amplitude, pulse shape, all on the fly using the 6 gigasample per second transfer rate that a Proteus can do, is certainly a good tool if you're interested in radar development. So let's just go through the block diagram to conclude. We have 4 digital to analog converters within each module. We have 2 analog to digital converters. We have the FPGA system here, which does a lot of the management of the streaming, allows you to set the different DAC rates. It looks after the waveform memory, and it also has the decision blocks features, which allows you to program it. We have this high-speed Gen 3 interface that allows us to stream or even just push waveforms into memory as other waveforms are playing out. That's per module, and you can hook multiple modules together. As you can see here in the PXIe version, we can have many channels of operation. So if I'm designing a N by M MIMO system, I could have many channels, and I can control each channel's phase and amplitude or weight them in whichever way I want. I could stream that real time. I could make the adjustments, phase and amplitude or time and amplitude very fine, or I could do it coarsely. And that's not only good for MIMO. If you're doing angle of arrival, for example, in electronic warfare systems, 4 channels you could feed to a radar warning receiver, and you could create different scenarios of angle of arrival with different threat models. If you just need it on a bench, you can have either 12 channels of arbitrary waveform generation, or you can have 8 channels of arbitrary waveform generation and 4 channels of digitization, all in the same unit, which is a nice, easy to use GUI with a keyboard. Again, if you're the cost-conscious person and you've got your own keyboard and your own screen, you can forego the screen and just get the modules themselves in this, what we call desktop version. So this is a desk and this is a bench, and this is the PXIe version. So the Proteus family. It's been designed for wide bandwidth direct to RF signal generation analysis. I hope you enjoyed this brief teardown of the instrumentation, and I'll open up the floor for questions now. Thank you.